Hello and welcome to today's session. This session focuses on learning outcome 3 LO3. Understand the reactions of alkenes. In this video, we will explore why alkenes are more reactive than alkanes, examining their unique chemical properties and behaviors. Join us as we uncover the key reactions of alkenes and the role of the carbon-carbon double bond in determining their reactivity. Alkenes are unsaturated hydrocarbons with at least one carbon-carbon double bond. This double bond consists of one sigma bond and one pi bond. The pi bond is weaker and more exposed, making it reactive. This reactivity allows alkenes to undergo addition reactions. Electrophiles are attracted to the electron-rich pi bond. Alkenes, like alkanes, can combust. In complete combustion, alkenes react with excess oxygen to produce carbon dioxide and water. Incomplete combustion occurs with limited oxygen, producing carbon monoxide or soot. Due to higher carbon content, alkenes create smokier flames than alkanes. This difference highlights their unique combustion properties. Addition reactions transform alkenes into saturated compounds. Hydrogenation adds hydrogen across the double bond using nickel as a catalyst. Halogens like chlorine or bromine react without UV light. Hydrogen halides produce haloalkanes, crucial in organic synthesis. These reactions showcase alkenes' versatility in chemical transformations. Alkenes can undergo addition polymerization. Small alkene molecules join to form long-chain polymers. Ethene forms polyethene, used in packaging and plastics. This process highlights the industrial significance of alkenes. Polymerization showcases the potential of alkenes in creating versatile materials. Alkenes can be oxidized using reagents like acidified potassium manganate. This reaction turns a purple solution colorless, confirming the presence of a double bond. It's a chemical test for unsaturation. This reaction demonstrates alkenes' chemical behavior. Oxidation reactions are valuable in analytical chemistry. A carbon-carbon double bond in alkenes consists of one sigma and one pi bond. The sigma bond is formed by end-on overlap of orbitals. The pi bond is formed by sideways overlap of p orbitals. The pi bond is weaker and more reactive. This explains the reactivity of alkenes. Alkenes exhibit geometric isomerism due to restricted rotation around the double bond. Cis, trans isomerism occurs in simple molecules. Z isomerism uses Kahn-Ingold Prelog rules for complex alkenes. Priorities are assigned based on atomic number. This system helps identify isomer configurations. Alkenes undergo electrophilic addition due to the electron-rich pi bond. Electrophiles are attracted to high electron density regions. The mechanism involves breaking the pi bond and forming a carbocation. A nucleophile then attacks the carbocation. This explains the formation of specific products. When unsymmetrical alkenes react with unsymmetrical reagents, two products are possible. Markovnikov's rule states that hydrogen attaches to the carbon with more hydrogens. This predicts the formation of the more stable carbocation. The rule helps determine the major product. It is crucial in predicting reaction outcomes. Bromine addition turns orange bromine water colorless, testing for unsaturation. Hydrogen bromide addition produces haloalkanes. Hydrogenation uses nickel to produce margarine. Water addition produces alcohols. These examples illustrate the diverse reactions alkenes can undergo. Addition, polymerization joins many alkene molecules into long chains. Monomers are the small alkene units. The polymer chain retains all atoms from monomers. High pressure and temperature facilitate polymerization. This process is key in producing various plastics. Each polymer's properties depend on its repeating unit. Polyethylene is used in packaging and plastic bags. Polypropylene is used in containers and ropes. PVC is used in pipes and electrical insulation. These polymers have widespread applications in everyday life. Many addition polymers are non-biodegradable. They accumulate in landfills and oceans. This poses a threat to wildlife and the environment. Incineration can release toxic gases. Recycling and biodegradable alternatives are crucial responses to these issues. Ethene reacts with hydrogen bromide in electrophilic addition. The pi bond attracts the hydrogen ion, forming a carbocation. A bromide ion then attacks the carbocation. This forms bromoethane, converting the double bond to a single bond. This example illustrates the electrophilic addition mechanism. Electrophile accepts an electron pair. Carbocation is a positively charged carbon ion. Curly arrows show electron pair movement. Electrophilic addition involves electrophile attack, carbocation formation, and nucleophile attack. This mechanism explains alkene reactivity and product formation. Addition, polymerization joins alkene monomers into polymers. The pi bond breaks, allowing monomers to link. No atoms are lost during the reaction. High pressure and temperature aid polymerization. This process creates versatile materials used in various industries. Addition, polymers are often non-biodegradable. They persist in the environment, causing pollution. Incineration can release harmful gases. Recycling is limited but necessary. Developing biodegradable polymers is a key focus for sustainability. Addition polymerization forms polymers by breaking carbon-carbon double bond. No small molecules are lost. Resulting polymers have widespread uses but raise environmental concerns. Recycling and biodegradable alternatives are crucial. Understanding polymerization helps address these challenges. Conclusion: the exploration of alkene chemistry highlights their pivotal role in organic synthesis and industrial applications. Understanding their reactivity, mechanisms, and transformations provides a foundation for further study and innovation. By engaging with this knowledge, one can appreciate both the theoretical significance and practical potential of alkenes, encouraging continued investigation and application in the field of chemistry. For support or questions, reach out via WhatsApp at 07484361688. We're happy to help. Thank you and see you in the next session.